Hello, this is the Senior Design Showcase video for the Contaminant Movement and Deposition Processing team.
Contamination introduced during semiconductor manufacturing can lower device performance and increase reliability concerns. The mobility of contamination within a device can create field failures, which creates huge product quality concerns. Our project focuses on a specific contamination that is introduced when creating a tungsten interconnect. Tungsten is deposited by chemical vapor deposition. During this process, fluorine is introduced as a precursor gas and leaves a concentration of fluorine in the deposited tungsten. Our project was to create a model using COMSOL that shows the effectiveness of titanium nitride diffusion barriers and how barrier thickness affects diffusion. The image on the left shows a typical tungsten interconnect with a tinitride barrier, and the image on the right shows a resistive interface that is caused by fluorine diffusion.
Our approach to solve this problem implemented COMSOL. COMSOL is a mathematical modeling software that drives new breakthroughs in physics and engineering. The first step in creating a model in COMSOL is to define the geometry. The geometry is the structure that houses all the physics and reactions that produce the final physics calculations. The next step would be to select the material from COMSOL's material database. And our third step is implementing transport or diluted species module. This module was key to setting initial and intermediate concentrations within the model and allowed adjustments of how the contaminants move through different barriers in the design. And this is pictured on the right with the brightly colored model. The final step is finite element analysis, which is used in creating the mesh. This breaks the model up into small pieces that calculate independently, resulting in a complete analysis, as pictured at the bottom right.
In order to gain further understanding of fluorine migration in real-world settings, our sponsors processed 6 wafers consisting of various thicknesses of silicon dioxide, tinitride, and tungsten. These wafers were then annealed at 400C, 650C, and 900C for 30 minutes, and then analyzed using secondary ion mass spectrometry, or SIMS for short. SIMS is an analysis process that uses a sputtering technique and a focused primary ion beam to capture the mass and charge of ejected secondary ions. Measurements are done with a mass spectrometer, which determines the elemental, isotopic, and molecular composition of a surface depth of around 1 to 2 nanometers. The resultant data, when graphed, looks like the one below. Comparing the data to our model was key to verifying how well our model works, demonstrating what is happening during diffusion through the layers of the physical wafers.
So when bringing it all together, what we did was we took our physical model that was created with materials assigned, dimensions laid out, and physics applied, and tried to put the SIMS data onto the model using the diffusion coefficients derived from the SIMS data. Our initial goal was to use this coefficient and apply it to our model and see how the fluorine diffused through in real time. Unfortunately, the data from the SIMS has a degree of randomness to it. This contradicts the COMSOL way of modeling. When COMSOL applies physics to a model, the values are fixed to be perfect. As we can see on the graph to the left, the diagonal line in the model represents perfection, which is unobtainable in real-life application. The graph on the right is more accurate representation of the actual data, which shows a gradual curve of fluorine penetrating into the barrier and subsequently into the substrate.
Because we couldn't match our real-world data with COMSOL and we couldn't get the diffusion coefficients, we decided to use the SIMS data to get a better understanding of what was happening during that annealing. As we can see on the graph on the left, the concentration decreases along this curve as we approach the barrier. So what we did is we tried to match that within our model. So we added a couple more layers of tungsten within our model and we changed the diffusion coefficient until we could get this better demonstrated curve that you can see on the left side of the right graph. With this, we determined that the grain sizes decrease as you get closer to that barrier, which increases diffusion. And this we also verified with our sponsor, and they said that that makes sense as to what was happening. In terms of our final model, we weren't able to get one with accurate real-world diffusion coefficients, but we got a model that when the barrier size increased, you can see that the diffusion was slowed down, shown by the more yellow color within the tungsten pieces of this model on the right.
We'd like to acknowledge all our sponsors from Micron Technology and faculty from Boise State MSc Department. And if you'd like more information, please join us for the Senior Design Showcase. Thank you.